Okay, we come to the question that everybody that's talked to me has about a basis, or at least the dimension, of the vector space consisting of 6 by 6 symmetric matrices. Okay? Now, I don't really want you or expect you to reason this out in terms of 6 by 6 matrices. At least not the first time you see it. I mean, some people maybe can, but that's going to be beyond most of us. First of all, we have to get a handle on what symmetric means, and I'm finding that people don't have a very good handle on that. Symmetric matrix is a matrix that's equal to its transpose. Its transpose is what you get when you switch its rows and its columns, which means that a matrix is equal to its transpose. The only way that can happen is if the numbers above the diagonal are mirror images of the numbers below the diagonal. And that's something I would hope that everybody would have worked out by now, but it's not that hard to work out. You want to think that through, make sure you understand that. So, now, I don't want to think about this for the set of 6 by 6 matrices. I want to get a handle on this by first just considering M22, the simplest set of square matrices. Also, let's note that if a matrix is symmetric, it's got to be square. It's got to have the same number of rows and columns, because when you switch rows and columns, it's got to be equal to itself, and if one or the other is longer, it's not going to work out. Okay, you can work through that. Okay, I want to think first of M22 and talk about the dimension of M22, because we need to understand this before we can have any clue about M66, or the set of symmetric matrices within M66, which of course is where the set of 6 by 6 symmetric matrices would live. So a standard thing in problem solving is, I don't want to think about 6 by 6. I'm going to go to 2 by 2 and see what I can understand there. And then maybe I'll go to 3 by 3. Maybe I'll even go to 4 by 4. By then, I'm hoping I'll see a pattern that can extend to 6 by 6. Okay, well, so we think first of M22. What's the dimension of M22? Well, we want to write down a basis for M22. Now, some people were able to tell me a basis pretty quickly because, of course, one of the things we were assigned to do was write down a standard basis for such spaces, for polynomial spaces, for matrix spaces, for spaces of functions, in addition to spaces for Rn. Okay, so a basis of M22. Well, the student came in and asked me this question, was able to pretty much tell me after we got across, we're talking about matrices, and the matrices are treated as vectors in distinguishing a 2 by 2 matrix from an R2 vector, okay? So we got this pretty quickly, but let's see how this works, okay? If I have these 4 matrices as my basis, and those then are going to be said to be in this order, the vectors V1 through V4, okay, well, what's our general vector in M22? Well, it's a general matrix 2 by 2, so we could write that as just A, B, C, D. Okay? So if V equals A, B, C, D, now remember this is a vector, but it's not a vector in R2. It's a vector in the vector space M22, and it's a perfectly good vector. That looks a little weird, calling a vector something that's got all these rows and columns, but that's the way it is. Anyhow, if V is this, then we want to be able to write V as a C1 V1 plus C2 V2 plus C3 V3 plus C4 V4. How do we do that? Well, what multiples of these 4 basis vectors would add up to this? It's fairly straightforward. If you haven't seen it, stop and think about it before you look at it. But if I multiply A times the first matrix, I'm going to get an A here. If I multiply A times the second matrix, I'm going to get a B here. if I multiply B by the second matrix, I'm going to get a B here. If I multiply C by this matrix, I'll get a C here. If I multiply D by this matrix, I'll get a D here. And if I add them all up, I'm going to get this vector. So it's fairly straightforward that if C1 equals A, C2 equals B, C3 equals C, C4 equals D, this vector, relative to the standard basis, is A, B, C, D. That is that A times V1 plus B times V2 plus C times V3 plus D times V4 equals the vector V. Okay? And that's what it means. Okay? And that's what we mean by a vector relative to a basis. Now, all of a sudden we're in R4 here with this vector. Well, it is identified with a vector R4, but it's this matrix represented relative to this basis. And this is how we represent a vector relative to its basis, by the components, the numbers that you would have to multiply by each of the basis vectors in turn in order to get this. Okay, you might have to wrestle with that a little bit. Well, now we proceed to try to figure out what would be a basis for the set of symmetric matrices, and we had to, work a little bit with, okay, which of these are symmetric? Well, don't look down here, look up here. Which of these do you think are symmetric? And you should stop and think about this before I tell you. Okay, well, I'm telling you, so hopefully you stopped until you got it. But, okay, is this matrix equal to its transpose? Is this matrix equal to its transpose? What about this one? What about this one? As an example, this matrix is not symmetric because its transpose is this. Its first row is the first column of its transpose. The second row is the second column of the transpose. These are not the same. This matrix is not symmetric. Transpose of this matrix is, well, first row becomes first column, second row becomes second column, and we get the same matrix. These are equal, so it's symmetric. Another way of looking at symmetry, of course, is what's above the diagonal is the same as what's below the diagonal. There's a mirror image of what's below the diagonal. Okay? So, what's your general symmetric matrix? How would you write the general symmetric matrix? Now, we've got a general 2 by 2 matrix written A, B, C, D. So, using letters, what's the form of a general symmetric matrix? Again, you should think about this and not just memorize what I tell you. You should be able to get this, I hope. But, not everybody gets everything. I don't get everything first try. Okay, well, what's on the diagonal is going to stay on the diagonal when you switch rows and columns. So that the diagonal is not going to matter. So since I used A and D for the diagonal elements here, I'll use A and D for the diagonal elements here. Okay? Your general symmetric matrix can have anything at all on the diagonal. It's what's above and below the diagonal that has to match up. So, if you put B here, okay, well, when you transpose this, this row becomes your column and the two have to be equal. Well, if this row is a column of something that's equal to it, you're going to have a B down here in the 2, 1 position. So I'm going to say your general symmetric matrix has this form. Now we want to get a basis. For symmetric 2 by 2 matrices. How do we do that? Well, let's look up here and see which ones of these could go into that basis. These matrices form a basis for all of M22. Maybe we can take a subset of this sat and get a basis for these symmetric matrices. Turns out we won't be able to, but we can use some of them. And we can use any of them that work, and then we have to figure out what else to use. Well, this is symmetric, so we can use it. Now, let's just do that. Okay, we got 1, 0, 0, 1. This isn't symmetric. We can't use it. This isn't symmetric. We can't use it. This is symmetric, so we can use it. Okay? Now the question becomes, can we get this matrix for just general, any old number, A, B, and D, because there are only 3 numbers here, can we get this matrix as a sum of multiples of these 2 matrices? Think about that question. Well, hopefully you did. And yeah, I've got a penchant for writing ones where they don't belong. This matrix is clearly this, okay? The matrix I wrote is symmetric, and it would actually work just fine with this one, but it's much simpler if I've got just a single 1 in the matrix, because then it's easy to match up multiples that give us whatever matrix we're after, okay? So, well, using this matrix, if I multiply this matrix by A, I'm going to get an A here. If I then multiply this matrix by D, I'm going to have a D here, and so if I add A times this plus D times this, I'll have my A and my D. Okay? Now, how am I going to get B? That's worth stopping and thinking about. You'll learn better if you do, but don't spend days on it. Okay, so, okay, well, hopefully you've seen it. We can add the matrix with a 0 here and a 1 here. The matrix has to be symmetric. Now, we have to have something here in order to get a number here. We're not going to get a B here unless we have a 1 in this position to multiply our B by and add to whatever to the A and B multiples of these 2 in order to get a B here along with our A and D. But we also have to get a B here. Well, this is what we're going to be multiplying by B, so I'm going to put a 1 here, and to keep it as simple as possible, I'm not going to put anything, I'm only going to put zeros where I don't absolutely need ones, okay? And I'm not going to use numbers other than 0 and 1 because the arithmetic is just simpler. Well, I could. This could be 15, 0, 0, 0. This could be 0, 0, 0, 48. This could be 0, square root of 2, square root of 2, 0. But then trying to match it up with this form would just be a little more complicated. Okay, so now we see that if I do A times this plus B times this, A times this plus D times this plus B times this, I get my general matrix.